Now we're going to look at how we could set up triple integrals using orderings other than just dz, dy, dx. And when you might want to do this, I have a sketch here of an example where this might be useful, is if you had a similar shape to what we did in example one, but it's just rotated on its side. And in this case, if we wanted to set it up analogous to what we did in example one, it would make sense to integrate by first freezing both z and x and shooting this arrow parallel to the y-axis. So my integrand, my inside integral would be with respect to y now, and it would be like my lower surface. I'll just call the lower, oh, okay, lower is going to be weird because it's more like left and right. Let's call this one y is g1 of x and z, and then here I have y is g2 of x and z. And so those would be my left and right bounds, which are going to translate to my bottom and top bounds here. And then my integrand's the same, so my integrand's just some function. And then to get the next bounds, I could either do dz dx or dx dz. And either way, I'm going to be, let's say we just do dz. And then dx. So I'm going to leave these here blank because we're going to do a specific example, but really what I would be doing is figuring out that region in the zx plane. So if this is x, this is z, and this is my region R, I would use these bounds to set up these outside two integrals as if it was just a double integral over that region. So let's do a full example on this. Let's actually go back to our warm-up and add in a little bit more info. Okay, so we have this region we had on the warm-up, and let's actually put a picture because we already graphed this as part of the warm-up. Move it. Let's put it up here first. Okay, and so in the picture, we can see that this top surface is coming from this plane. Okay, let's also label. This is x, this is y, this is z. And so here I have z is 4 minus y. And then this side and the other side are on the back. This is coming from y equals x squared. Okay, so let's rewrite what we found in the warm-up. We found the volume of this using a double integral. And recall when we're using a double integral to find volume, that my integrand is actually going to be the top of the region. Okay, so now we're going to see how we could set up this volume using a triple integral instead and why they give us the same result. So now for the triple integral, recall what it means when we're using a triple integral is that we're chopping up this region into these, oh, let's make it a little bit higher, like into these little rectangular boxes anywhere inside here. Try to make it right. And the volume of one of those little boxes is dz, dy, dx. So if I want the total volume, I'm just going to be adding up a bunch of these little boxes inside here. And I'm going to be adding in 3 dimensions because they have an x, y, and z, which I'm adding them in. And so my integrand in this case is just going to remain 1 because really all I'm adding are these, which are the volumes. And here, let's erase this so we can. Okay, so to figure out my bounds, I look at the inside variable first. If I'm integrating with respect to z first, it means I'm going to shoot an arrow through this region with x and y frozen and see where it enters the region and where it exits. And we can see it's going to enter along the xy plane when z is 0, and it's exiting along the top plane 4 minus y. And then the shadow of this region on the xy plane is going to be exactly the same r that we did in the warm-up. It's just this region right down here. So those bounds we've already found, those are the same bounds here we found in the warm-up. So it'll just be x squared 4 and then negative 2 to 2 for x. And notice why these end up being equivalent. If we just start doing this integral on the right, when I integrate 1 with respect to z, I'm just going to get z from 0 to 4 minus y. And then I still have those outside integrals left to do. Okay, so notice as I simplify this, that this is literally just going to become exactly what I had over here, because my integrand, let's just do this integral, this one, and my integrand is just going to be 4 minus y minus 0. And then I will have dy from x squared to 4 and dx. So these are the same. And you may be wondering, well, if I could have figured out the volume using a double integral, why bother with triple integrals? And this is really a special case because you can't find the volume of all three-dimensional objects just using a double integral. In fact, the object has to have a very special property in order to be able to do it using either a double or a triple. Can you see what that property is? What's the property that this surface has that our earlier surface did not have? The one that we just did in the previous example. Let me find that one. Remember this surface, we needed to find the volume, and there wasn't a way to write it in terms of just a simple double integral until we had actually started doing some of the math. Like once we set it up this way and then we started integrating, this triple integral did become a double, but I still had to set it up as a triple to start. And the difference is my lower bound in this picture is some surface that's not the xy plane, as opposed to my lower bound here is just the xy plane. And so if your lower bound is the xy plane, your integrand, when you're coming to find the volume, integrand of your double integral will just be your top surface, 4 minus y. And so you can quickly just find the volume with the double integral if your lower bound, or if your lower bound of your region is the xy plane. Now, the other reason that we're going to still want to be able to use triple integrals, even with a region like this slice of cheese, if that's what you want to think it kind of looks like, is let's suppose I give you the density at any point, which we do in this problem. I tell you the density at any point is x to the 4th y grams per centimeters cubed. And then I could ask you, what's the mass of this total object? And now there's no way to do that using a double integral, because I'm going to need to chop up these into little volume rectangles here and estimate the mass of one of those little volume rectangles as being my density times the volume. And so that's going to require that I actually add up in 3 dimensions and I have a triple integral. So let's do that next. And let me rewrite my density so I don't forget. Down here, suppose I have, so given, let's write it above here. Given density x to the 4th y, I think grams per centimeters cubed is what I had up above. Let's set up integrals to find the mass. Okay, so in general, the mass of this 3-dimensional region is going to be a triple integral over the region of the density. So this. Okay, and let's try 2 different ways of setting it up. So let's put some pictures here so we can use them as visuals. Let's put that here and start with dy, dx, dz. All right, if I want to set this up using this ordering, my integrand will stay the same. That's not going to be affected. But then I'm going to have dy, we'll figure out what these limits are, dx and dz. So take a minute and see if you can put it on pause and figure out what your bounds would be as we're using this ordering, dy, dx, and dz. Put it on pause while I'm writing the rest of this out and see what you come up with. Okay, so let's do this from the picture. And here, as a reminder, this is x, this is y, and this is z in the picture. So if I'm integrating first with respect to y, what I'm really doing is freezing x and z and shooting an arrow parallel to the y-axis through my region. So let's have this thing come shooting through. And I'm going to look at where it enters and where it exits. And it may even help. Maybe I can slide it over a little bit so it there kind of is coming right through there and there, so you can see, because I can shoot it anywhere in the region. Notice it's no matter where I choose to shoot this arrow, it's always going to be entering along this y is equal to x squared, which is this yellow surface. And it's always exiting, in this case, along this plane, which, let's go back above. Sorry, this is hard to see on here. The plane is given by y plus z is equal to 4. So that's going to be, let's write that, y plus z is equal to 4, and this is y is equal to x squared. Okay, so if we solve this equation for y, I'm getting 4 minus z up here. Let's move this down a little bit so we have some more room. Well, that didn't help. Okay, I'll move it in a second. But now I want you to think about what the shadow is going to be. So take a second and see if you can trace the shadow on the xz plane and figure out what your xz bounds will be. So here's x, here's z. What's the shadow of this region going to look like? All right, and let's look at this in Mathematica also, because this should help. I'm now going to turn it back so we're just looking at the xz plane. So you can see that the shadow should be this type of parabola. And what's causing the shadow is the intersection of the two surfaces, the intersection of this plane and this y equals x squared surface. So let's go back and find that algebraically. All right, and so this intersection we can see on the picture. Let's find the actual equation for that just in the xz plane. So I'm going to set y plus z equaling 4 and y is equal to x squared, which is going to imply that x squared plus z is equal to 4. So I can plot that. Here's the parabola. I'll just plot it for positive z. This is z is 4 minus x squared. Okay, so that's going to be our shadow on the xy or on the xz plane. Let's color it in. And now we're going to use that to figure out our bounds for our outer two integrals. So because I asked you to integrate next with respect to x, that means that you're going to shoot an arrow parallel to the x-axis because you're chopping that way first, and you're going to look at where it enters and exits. So we need to solve this equation for x, and this is going to give me that x is plus or minus square root of 4 minus z. So it's going to enter along that left side, which would be negative square root of 4 minus z. It's hard to see there. I can fix that in a minute. And this is positive square root of 4 minus z. And then my z limits are going to be the smallest and largest z values in this region. And so z has a smallest value of 0 and a largest value of 4. And as a reminder, your outer limits for any integral, double or triple, are always going to be constants. Okay, so why don't you go ahead now and put this on pause, and I want you to try to redo this with a different ordering, dx, dz, dy, to see if you have been able to visualize this. Okay, so for this one, we are still using the same picture here, but now what we're going to do is start by shooting parallel to the x-axis first. This is going to be a little bit tricky to show, but I want to picture it coming in behind there and then coming out like this. And so you can see that's entering along the back of the yellow surface. That yellow surface is given by y is x squared. So the back of that surface has to be x is negative square root of y. And the front of this surface, this side right here, is x is positive square root of y. And then we need to think of the shadow that we're going to get now on the zy plane to figure out my outer two bounds. And you can notice what's causing the shadow is actually just this plane here, and where that plane intersects the y-axis and the z-axis. So that's coming from, this has to be 4 and 4 because this is the plane y plus z is equal to 4. And this is going to be my region R. And we can also look at this in Mathematica if you want to see really quickly how that's actually the shadow. Let's click on that real quick. Right, so if we turn it and and now we're just looking right from here, you can see that shadow is just going to be that triangular region, and it's caused directly by the plane. Okay, so let's go back and find the bounds now. All right, so I specified the order dz first, so that means you're going to be shooting an arrow parallel the z-axis and looking at where it enters and exits your region. Here you can see it's entering when z is 0, and it's exiting when z is 4 minus y. So those will be the bounds. And then y, again, are going to be the smallest and largest y values where you could have shot your arrow through. And so the smallest possible y value where I could have done that is 0, and the largest is 4. So y is just going from 0 to 4. And you can calculate either of these, we'll get the same result for the mass. It ends up being some pretty complicated value. So for this point, I just wanted you to set it up and not actually go through all that algebra of that integral because it's pretty algebraically intensive.